Hello everyone. In this video, I'm going to show you how to build a soft-core NIOS CPU in the Intel Altera Max 10 FPGA. This is part 3 of the soft-core CPU series. Previously, we have demoed how to build microblades and RISC-V CPUs in Xilinx FPGA. I have video links in the description below. You can watch the other videos follow the links. NIOS 2 Embed Processor is also RISC-I SC-based soft-core CPU. You can get all the informations referenced in the Intel's website. In this video, I'm going to use the Max 10 evaluation board based project. Last time we used this project to demo the Intel workflow. I'm going to build the NIOS core step by step and then use the NIOS Eclipse tool to program the software layer. Now let's start. As you can see, the project's top file is pretty much all the pins, I/O, and simple codes checking the version, checking the crystal clock frequency, and toggle the LEDs. Very simple. Now we'll bring the platform designer. Quartus platform designer is pretty much like Vivado's block design, but not like the graphical block diagram workflow. In this platform designer, you will need to understand the components in the connection very clearly. All the candidate connections list on the left side, and then you connect them together manually. The platform designer creates the IPs in a wrapper. First, it brings in the clock and reset. Those clock and reset are exposed to outside world on the edge of the block. Because the clock input is the Max 10's crystal direct input, we are going to add a PLL to buffer and smooth the clock. The input crystal frequency is 15 meg. All the others are just normal. And then we will create a 100 meg clock for the NIOS and the Avalon bus. We also create a 50 meg clock as the buffer option of the crystal to clock the peripherals and the external fabric. Now you need to connect the clock output from the clock block to the PLL input and the reset. The platform designer reset connections is quite automatic. If you want to double check the polarity of the reset, active high or active low, you can check in the pins here. If the name has the N, it's active low. If the reset doesn't have the N in the name, it's active high. So the platform designer will automatically insert revert component between this reset to properly adapt the active high or active low requirement. The clock output, we are going to bring it to the fabric. So right now we want to have a clock bridge. The clock bridge will input from the PLL output and bring the output to the external. Now we will add the NIOS. NIOS 2 embedded processor. The two kind of processor, one is the E version, which is an economy version that uses less resources in the FPGA, or you can build the F version, the faster core that has higher performance. For the simple demo, we just use the E version. The vectors, right now we don't have any memory attached to it, so we can go back to here later. Basically, the reset vector is the boot vector that when you boot, the CPU run the instruction from here. The exception is handling the interrupt or things like that. All the others seems to be just leave as is for now. So we are going to connect the clock to the 100 meg, the reset. As you can see, the two Avalon buses master, one for data, one for instruction, they're already connected to the debug slave. Now we need to add some memory, RAM, to the NIOS. We are going to use the on-chip memory. It's just used as the RAM. The size of the RAM, the M50 Intel Max 10 contains about 130 kilobyte memory. For the minimum requirement for the NIOS to run, just bare minimum print out something like hello world, we need around 30 something kilobytes, so we just assign 64 kilobytes here. The memory needs to be attached to the Avalon bus, both the data and instruction, and the clock use the same 100 meg, reset goes the same. We will also need to add on-chip flash to hold all the software layers binary in the Max 10 itself. The on-chip flash has some configuration mode. This has to be matched with the project settings. For example, right now the project sets to single uncompressed image. We can change to single compressed image to give a little bit more space for the flash to hold the software layer. Then in this NIOS flash setting, you will also need to set it as a single compressed image. We'll change all this to read-write available. So all 5 sections of the flash, one holds the fabric bitstream, the other 4 holds the software layer. This on-chip flash also needs to be attached to the memory master. The status also needs to add it to the data master. Clock is the same, reset is the same. So for demo purpose, we are going to add a UART to this NIOS as general I/O. We just use the Intel UART core. Just leave as is. For the purpose of running the slower speed peripheral, we just need to change the Avalon bus clock from 100 meg master to the 50 meg to run the peripherals. For that purpose, we need the clock crossing bus. Just let the address assignment automatic. 32-bit wide, that's okay. We can move this block up a bit clear. So the slave clock, the Avalon clock crossing bridge slave is connected to the master of the CPU, so the slave clock needs to be 100 meg. Both slave and master reset connect to the same. The slave connect to the CPU's data bus. The master clock is going to use the 50 meg peripheral clock C1 here. So we just connect this to master clock C1. And the master is going to connect to all the slave bus of the peripheral. The slave clock is running 50 megs also. Not this one, this one. And reset is the same. The interrupt will be connected to the CPU to be functional. We also need to bring the UART I/O, RX pin and TX pin to the external. Now we have add the memory and flash to the NIOS. So we can go back to the NIOS configuration. We can assign the vector right now. The boot vector will be going to on-chip flash, and the exception will be used as on-chip memory. So setting the on-chip flash as the boot vector, meaning that after power up, the CPU will boot to the flash, and there's a small bootloader exists on the on-chip flash disk address. That program will copy the whole software binary into the memory. We can configure that in the Eclipse later. For now, the setting is fine. And we also use the system automatic assign address to this. For demo purpose, we are also going to add some parallel I/O to the core. The parallel I/O can be either input or output or bidirectional. You just make some 32-bit input and connect to the bus. And bring that to external. Then we add another output block, 32 also. And refresh the memory. So it's not very clear like block diagram, but connection wise You can double check all these connections up and down. Okay, we can save that for now. And generate all the HDL files. Now it's done. We can go back. Let's close this. Go back to the, you need to manually add this file to your project. Now, as you can see, in the NIOS IP folder, you will have an instantiate example. You can just use that, bring it to your top file. We will need some signal. The clock input of this block will use the evaluation clock input, and the reset button will connect to NIOS reset. Output bring back to the fabric. So external fabric use the clock from the PLL instead because it's buffered. The UART UX and the IOs So in the software layer, we are going to export the software version and connect to the prop file so that you can use the in-system prop to check is that software really running. And we are going to also bring the clock frequency to the input so that we can print the clock frequency in the UART. Each clock frequency takes 20 bits. Let's say take the ADC clock, 10 meg. And that's about it. Save. We can build the project. Okay, here comes some errors on the compilation. The internal configurable design memory initialization. Okay, here is the problem. Remember, we attach some on-chip memory and on-chip flash to the NIOS. One thing need to double check is that on-chip memory, the initialization content we don't need to specify here because we just use this as a RAM. There's no initialization file. The on-chip flash also don't need to initialize. Basically, when this configuration is set, we will need to combine the software binary and the fabric bitstream together in the same POF file and then load to the board. If you initialize the content in this design, then every time you change the software layer, you will need to recompile the fabric. Okay, the IP code updated, and then we just recompile again. Now the compilation is done, no problem. As you can see, the Quartus generates the NIOS hardware information. We are going to use this as the BSP information to bring in the NIOS Eclipse. Let's open Eclipse. Typically, you will just put the workspace in the software folder. So we're going to build the new NIOS2 application and BSP. We will select the information, just build from Quartus. It recognizes the CPU and all the I/O peripherals. You can just set that as a UART demo. Now, in the BSP configuration, you need to double check a couple things. So make sure the standard I/O is the UART we put in there. Sometimes if you enable multiple UART, it's probably going to the other one. And all bitstream reside in the flash and put to the flash and copy the whole thing to the memory. We need to double check here. So code reset here. And then if all this enable Altera load, Altera copy, read write, everything here, this enabling will make the binary code reside in the flash and run from the flash. Without that, it's just a minor bootloader to copy the whole bitstream into the RAM so you got run faster. Other than that, everything seems to be normal. Now we will build the NIOS. In the system header file, you can see there's a Altera CPU NIOS on-chip flash, on-chip memory. All the addresses indicates here, and the PIO block, UART block, so everything is defined in this header file. The basic demo only print the hello from the NIOS. We're going to replace it with the a little bit more complicated with the PIO stuff. So we changed the hello world C program a little bit, include these headers. The system H, as I said, define the address and how it's called. See the PIO base, PIO1 base, etc. And then we set the software version and get this version sent out to the PIO output on the last 8 bit. We input the PIO and get the frequency from the LSB 20 bits, and then print this to the UART and get the loop here. Pretty simple. You can find all the files in my GitHub. I provide a link in the description. So now we can refresh this. That's the file. And then rebuild the project. So to combine the software binary into Max10 POF file, we will need to also build the hex file for the binary, which is using here the memory initialization generation from this Eclipse tool. When you build this one, it will build the hex file. We're going to use it later. As you can see, the hex file is in the software project and the memory initialization folder, the on-chip flash hex here. So once this is available, we're going to combine to convert the programming file. So you will need to generate the POF file. The mode is internal configuration. And then we will need to bring that hex file here, load the memory file to the UFM source. Software project, the on-chip flash hex here. So once this is ready, we will save the output file and also add this FPGA bitstream here, the SOF file. Now generate the file. The file is in the folder where you saved the POF file, which combine all the bitstream binary and the software layer binary. So we'll copy this to the Max10 and program it. Now we connect to the JTAG of the evaluation board. Bring the programmer. Load the file. The programmer automatically recognizes the CFM section and the UFM section. Once it's done, it reboots from the flash and start running the program. Now we can open the serial port 8 It's printing the ADC clock frequency. 2710 is the hex number of 10 meg. If we do a reset, it's restart the count and the NIOS, so everything works as expected. That's pretty much it for today's video. Hope you like the video and see you next time.